So our next speaker is Vinayak Dangul. He's a network engineer at Meta. So his research interests are network planning, optimization, and modeling, as well as the use of machine learning for network optimization. Yeah.
Thank you. In this talk, I'm going to discuss our network entitlement system, which is a contract-based network sharing with agility and SLO guarantees. And I'm presenting this talk on behalf of my co-authors. So, as an outline of the talk, we'll first discuss the concept of entitlement contracts, then the host abstraction that we use to model the traffic from services, the bandwidth approval engine that we use to generate those contracts, the enforcement process of the entitlements, and a brief discussion of our operational experience in a summary. Meta's compute infrastructure is pretty broad. You have here the locations of our data centers, both online and under construction. So this spans an intercontinental network, obviously, for the backbone. And obviously, it's global compute that we need to optimize. What are some of the challenges that we experience? Well, to begin with, demand increases faster than capacity. In particular, we observe rapid growth in DC to DC traffic, spurred mostly by artificial intelligence workloads. Second, the network is a shared resource. What we mean by that is that services contend for capacity on the network, and therefore an outlier pattern in one service can have an impact on multiple other services. And therefore, it would be ideal if we could offer some form of isolation guarantees to the services in the use of the network. Finally, we want to be able to offer some form of accountability from the network to services. This indicates first that we need to be able to measure the performance delivered by the network, and finally create a clear contract for services based on SLO guarantees, ideally. And you have here an example of traffic growth, which is obviously much larger on the internal traffic than the one egressing to the internet. So we talked about the impact of services upon each other. In this particular example, there was a service bug that resulted in a traffic surge, as is observed here, and it impacted services in lower class of service. As can be seen here, the surge primarily hit the service itself, but also impacted other services and induced loss in the network. So we want to create these entitlement contracts. In terms of definition, this is a bandwidth contract that is offered by network engineering to services. The definition is predicated on a particular region, data center, per service or service group, per class of service, per direction in ingress or egress out of that region. The contracts are issued for a duration of 3 months, and therefore we define them as a tuple of service, region, class of service, direction, bandwidth, and end date. What does the contract translate into? If the traffic transmitted by the service is below the entitled amount in the contract, we will guarantee that the SLO of that class of service is met. Any traffic transmitted in excess is going to be transmitted as best effort. As a result, this is work conserving, but obviously there are no performance guarantees on excess traffic. And we achieve this through DSCP remarking at the host. What are some of the benefits from this? Well, service isolation is a built-in feature of entitlements. Second, this provides services with an abstraction that is specific to a region, right, not to a source-destination pair. Therefore, it is very similar to how they process compute and storage. And finally, there is a clear accountability through the means of SLO. What does the stack look like for this system? And this is obviously a very simplified picture, but we start with service demand forecasts, which are expressed as traffic hoses, the network topology at the beginning of that cycle. We go through the bandwidth approval engine to generate entitlements. Those are stored in an entitlements database and then consumed by Floodgate, which is the policy enforcement system. Usually we insert a stage of manual review after generating the approvals before actually pushing the approvals to Floodgate. And as I've said previously, we run this workflow every 3 months. Hose abstraction. This is similar to what we described in our paper for hose-based planning in the last SIGCOMM. But the idea here is that instead of expressing traffic as source destination flows, as a typical traffic matrix, we are going to compress it into ingress and egress forecasts out of every region. This is equivalent to transforming the traffic matrix into the sum of rows and sum of columns. And this provides us with bounds per class of service in and out of a region with multi-node hoses that capture other constraints, say like subsea traffic, subsea capacity constraints. Some of the benefits of the hose are obviously simplification. We specify 2 N hoses for N regions as opposed to N square source destination flows. There are efficiency gains by factoring the peak of sum versus sum of peaks. This is a much more flexible means of describing traffic constraints that takes into account possible compute movements by the services. And as I mentioned previously, this is abstracted for the services in a way that is closer to compute and storage. You see here the result of our forecasting for the hose demand, where we plot the CDF of the forecasted value versus the accuracy. We use the Prophet open source library with 3 components, the main trend, seasonality, and holidays, and a tree-based model for inorganic change with regressors based on the monthly forecast plus power, compute, and storage usage. So the takeaway from this slide is the model is actually pretty accurate. We introduced a further improvement to the hose model for increased performance and efficiency, and that is what we call a hose segmentation. What we mean by this is that a generic hose assumes no polarization in traffic, right? The flows can go to any possible destination. Observation of traffic in the network actually indicates that this is not always true, and instead, what we do is we split the hoses for ingress and egress hoses into 2 multi-node hoses. So instead of having a generic constraint on the traffic going to all possible destinations, we split the destinations into 2 non-overlapping sets, and the constraint is broken down into fractionally one fraction of the traffic going to one set, and the complement going to the complementary set. So the bandwidth approval computation in more detail takes in the network topology at the start of the approval cycle, the service demands as hoses, which then generate traffic matrices as per our paper in the last year's SIGCOMM. We then run through a phase of SLO-based risk assessment, produce approvals per region, per class of service, and then we disaggregate that at the level of each individual service. Now, the risk assessment will essentially model the impact of possible network states onto the ability of the network to route traffic. For the SLO-based risk assessment, we essentially compute whether the network can meet SLO based on the Monte Carlo method. This offers to us guaranteed probabilistic bounds on the SLO that is achieved. We run this as a massive map reduce that is natively supporting hose. In under a minute of runtime, we can go through over 100 million network states. And the output is bandwidth availability curve per region, per class of service. As mentioned previously, we need to disaggregate that per services, and we break down services in broadly 2 categories. Low touch, which are aggregates of many services that are each individually too small to justify their own entitlement. This represents roughly, for each class of service, less than 10% of the overall traffic volume. And high-touch services that are large consumers of bandwidth and therefore have their own dedicated entitlements. In the disaggregation process, the service, low-touch services are granted their entitlements first, and then high-touch services receive their entitlements on the remaining bandwidth in the class of service in max-min fair fashion. One improvement we had to make is what we call the demand approval equalization. As we started running this process more and more often, we realized that some regions were experiencing saturation. which means that the amount of approvals we could generate was lower than the demand, sometimes potentially significantly. That is expected because, again, demand runs faster than the capacity we can build. Depending on the topology and the amount of saturation, we found that we could trade off actually approvals between different regions. And the equalization algorithm essentially relaxes the demand to the level of the approvals granted in some saturated regions in order to free up capacities in other saturated regions. We found gains of typically well over 30% in deeply saturated instances. So now we come to the enforcement of entitlements. And there we have multiple options. We can either shape, drop, or remark the excess traffic. We can do this at the granularity per packet, per flow, or per host. We can enforce at the host level or the network level. And we can use a centralized or distributed mechanism. So a lot of options. The legacy and initial solutions used a centralized architecture and throttling or shaping mechanisms. It was purely host-based enforcement, and initially a naive stateless algorithm and a classification per flow. The experience in prod and operation was quite poor, and this was discarded in favor of what we call floodgate, which is a distributed architecture with traffic remarking, therefore being work conserving, classification at the host, and enforcement at the network level, with an algorithm that uses the local state and per host classification. Here's a system view of it, where the application will transmit traffic through TCP/IP. At the same time, there is a user space agent that queries policies and aggregated counters, interacts with BPF maps, and through BPF will perform DSCP remarking of transmitted packets. Here's a result on the enforcement in the absence of congestion. So this is a 10-day window of a service in production. And as you can see, the traffic sort of goes up and down, and the conforming rate is always met when expected, and traffic gets remarked when non-conforming. And therefore, floodgate is work conserving in that situation. Now, we did a real-life congestion test, which is detailed in more details in the paper. But in this instance, we considered cold storage as a service. We ran on tens of thousands of hosts out of a region. And we reduced the entitlement rate of the service so as to increase the amount of non-conforming traffic. We then used ACLs on the network switches to essentially be able to adjust the drop rate on non-conforming traffic. So that was a good way to mimic network congestion, and we went from 0 to 12.5% drop rate, to 50% drop rate, to 100% drop rate on non-conforming traffic, with transitions roughly every half an hour, and we then reset everything to 0%. And we measured both the impact at the network level as well as at the application level during the test. So you see here 3 charts. The loss on non-conforming and conforming traffic, the rate transmitted, again, for conforming and total rate, and the RTT. And for each of those, we have takeaways. The first chart tells us that we have a guaranteed performance for conforming traffic, regardless of non-conforming loss. We can see here that there is no loss on the conforming traffic, even as we increase the loss on the non-conforming traffic. The second chart shows that we remain around the entitled rate for the conforming traffic, even though we increase loss on the non-conforming traffic. And this tells us that even as we apply congestion, we meet the traffic rate for the conforming traffic. And the last chart shows no major impact on the RTT for conforming traffic, even as we increase the loss on non-conforming traffic. And therefore, we use our network resources efficiently. The packets delivered do not incur any significant additional delays. If we look at the application stats here with read latency, write latency, and block errors, what we see is as long as the drop percentage is below 50%, we see a small impact to read latency, and that's because of a host-based remarking. On write latency, there is a severe impact, even for small loss. But that's because of the stateful nature of write operations. And the last chart shows that the failure peak correlates well to the TCP scene errors. So what has our operational experience been? Well, entitlements enable service isolations. There's plenty of data that we've presented to show that. This means that spikes in one service are properly remarked as non-conforming traffic when they exceed their approval, which means no impact to other services. That was one of the key goals we aimed to accomplish. The entitlements are meant to fairly divide the network as a finite resource. And that is what we achieve, although the saturation can significantly reduce the approvals, somewhat artificially, and we needed to implement relaxation algorithms in order to maximize the approvals granted. The next point, the measurement of SLIs is important. One of the feedback mechanisms we need is to be able to measure the network performance, taking into account how services consume their entitlement and how they perform, to be able to verify that the system works properly. During steady state, we saw no remarking violations. We saw remarking violations without service impact because we are work conserving. And during capacity shortfalls, the host-based remarking worked well with the expectation of services failures. So this worked well within our existing infrastructure. So to conclude, the approach of entitlements offer contractual representation with rows and SLO, service isolation and fairness, efficiency through work conservation, resiliency because we have isolated and measurable service degradation during failures. We can efficiently and optimally compute our entitlements to a bandwidth approval engine through the use of an equalization algorithm. And Floodgate provides runtime enforcement capability at scale with simplicity and reliability for operations through distributed remarking. And one of the important operational metrics is the network SLI measurements at the granularity of the approvals granted. Thank you.
We have time for a quick question.
Thank you for a good talk. So, according to what I saw, on the BPF path, you're actually marking the packets according to their arrival, right? Have you thought maybe to, instead of just when you get to the quota, you just mark it differently, to let the application decide about important packets and less important packets, and therefore reserve those conformant flows to actually go through, and not just in a way of just a threshold?
If I understand your question correctly, you're suggesting letting the application itself decide which packets to remark within the quota.
Exactly.
That's an interesting question. That is not the approach we have taken, but it echoes a little bit of the experience we've had and some of the feedback we've had. Maybe it's a question we can take offline.
Sure, thank you.
Thanks, Vinay.
Thank you.